So when you look at this one, the first one, carbon, remember if there's only one of the first element, you don't have to put mono. Okay, so you can just use the whole name of the element, first part of the second element plus IDE, but you do have to include the number no matter what for the second element. So that one is a dioxide. Carbon with 2 oxygens. So that's what the formula tells you. So CBr4 would be, yeah, carbon tetra bromide. Remember, tetra's the weird one. Tetra's the 4. I mean, it means 4 of them, so not quad. So tetra, keeping up with that one's fun. N2O4 then. Dinitrogen. Tetroxide. NH3. Nitro. Yep, try what? What's the hydrogen? So you take the first part of hydrogen plus IDE, so it's hydride. Okay, not hydroxide, because remember that's the OH. So that's that polyatomic ion. So this one is hydride. So an oxygen is the oxide, hydrogen is a hydride, bromine is a bromide, chlorine to be a chloride. H2O2, dihydrogen, dioxide, also known as hydrogen peroxide. So there are some that have like those like sort of common names to them. NH3 is ammonia, H2O2 is peroxide. But this is really their technical name if you were going to name them as a binary covalent molecule. So the last one. Trifluoride, okay, because of the 3 fluorine. So you always with that second element, first part plus IDE, but you do include that number.
We have a sheet with the the suffixes, don't we?
You mean that?
Yeah.
Yeah.
Well, the pre and the suffix.
Yep. So not the suffixes, but so like with those, always take for the second element. It's always the second element that you're going to do that. You just take the first part of its name plus IDE. Okay. So hydrogen is hydride, oxygen is oxide, nitrogen is nitride. So it's just like the first syllable of the second element and then add the IDE. And notice you're always seeing that. This is really like a naming that you use if you're talking about 2 elements. Notice this, CCl4, H2O2, H2O. It's just 2 different elements. So it's not like a whole bunch of different elements. It's only when you have 2 elements, they call them binary covalent. So binary just means that there's 2 different elements in the molecule. So that's where you would use those number prefixes. Now we were also doing the drawing part. So we did oxygen, we did carbon dioxide. Did you work on nitrogen? Nitrogen gas, 78% of the air. Nitrogen gas. 2 nitrogen atoms in a molecule. It's another one of those diatomic elements. Oxygen's a diatomic element. Remember hydrogen, chlorine, fluorine, bromine. They all exist as 2 atoms in one molecule. Well, nitrogen's another one. So nitrogen, how many electrons does it have? 5. So when you look, don't look at its atomic number. Look at the group number at the top. It's in group 5A. So that tells you there's 5 electrons. 5 electrons. That means to make 8, it has to have how many bonds? 3. Okay, so bonds plus electrons should equal 8, except for hydrogen. Remember, that one only needs 2. But all the other ones always need, so 3 bonds, 3 bonds. So if you just pick, like one doesn't need more bonds than the other, so you would pick a nitrogen, N, 1, 2, 3, 4, 5. Then do a single connection. Let me do a different color so you can tell. A nitrogen, 1, 2, 3, 4. And then you make the link between the 2. But that's all the electrons you can use. So the formula says it's N2. There's only 2 nitrogens. You can't add any more electrons, but you can pair them up. So that's when you begin to move in and move in between, move in between, move in between. So you're actually going to end up with 3 pairs between the 2 nitrogens, and that's a triple bond. So 1, 2, 3, and then over on the other side would be a nitrogen, and it would have 1, 2, 3 as well. So can you see how each nitrogen now has 8? It's 2 non-bonding plus the 6 it's sharing, 2 non-bonding plus the 6 that it's sharing. So you would draw this N, 1, 2, 3, N, with those non-bonding or lone electron pairs, 1 pair to each nitrogen. So CH2O, formaldehyde, go through, make the list: carbon, 4 electrons, hydrogen 1, oxygen 6. Remember that the valence electron number, you can find it by the group number at the top. So carbon needs 4 bonds. Hydrogens need 1 each, 1 and 1. Oxygen's going to have 2. It's what they need in order to have that 8. Okay, so you kind of get used to seeing it looking like that, but that's the rationale is always that it's going to have to share in order to have 8 total. So you always start with the atom that needs the most bonds. So which would you start with? Carbon. So you're going to put carbon down first. 1, 2, 3, 4. What atom next needs the most bonds? Oxygen. So add an oxygen next. 1, 2, 3, 4, 5, and pair. And it doesn't matter, see like the little purple and red dots, I put them either above or side by side. As long as the pairs are in between, it doesn't really matter if I have them like this or if I put it like this. The key thing is just make sure they're in between, okay? Because some people get really uptight about which way they lay. That really doesn't matter, okay? But notice in this, as long as I have 2 electrons between the carbon and the oxygen, that represents a bond. So now what do I have left? I've got 2 hydrogens. And how many like holes do you see? How many empty pairs do you see?
Oh, 4.
Do you see 4?
I'm sorry.
And I've only got 2 hydrogens. So that right there is going to tell you that this is like, we're going to end up having to make a multiple bond. Okay? Because that's the only way to pair these up. So where could I put the hydrogens so that it leaves me an electron on carbon and an electron on oxygen to form a double bond? Where could I put the hydrogens? So you want me to put one here? And then one where?
On the left-hand side of the carbon.
On the left-hand side of the carbon. Okay, so do you see that problem?
You still have the carbon.
Uh-huh.
I was talking about moving one of the dots to the
and so they could share with the center.
Okay, but those would be carbon's electrons, and why would it share that way? Why would carbon just share 2 electrons with oxygen just because it's nice? No. Where does that hydrogen, this hydrogen doesn't go here. If you put this hydrogen here, now do you see how the 1 electron from carbon and 1 electron from oxygen fits? So can you see how this can move over and this can move over, forming a double bond?
Oh, I see. Okay, that would be your double bond.
That's the double
Hydrogen
bond between the carbon. Hydrogen can't make a double bond,
Right.
right? Hydrogen's never going to have but just a single bond. They're always kind of like the ones that you fill around the edges. So the double bond's going to have to be between the carbon and the oxygen. So when we get done, we'll have the hydrogen down here. We'll have the carbon. It'll have a single electron pair shared between the hydrogens, but then 2 of its electrons will then share with the oxygen. So I just moved those in between, creating that double bond. And if you count, do you see that hydrogen, 1, 2, 3, 1, 2, hydrogen, 1, 2, oxygen, 8, and carbon has its 8. So if you're doing the dot structures with the lines, like that. Okay? Okay, so the last one's cyanide. Hydrogen,
One electron.
one electron, one bond. Carbon,
4 electrons, 4 bonds.
Nitrogen.
5 electrons, 3.
Yep. Remember that other than hydrogen, they always want 8. And so you're going to have electrons and bonds in order to create that. Which one do you start with?
Carbon.
Carbon. Carbon needs the most.
And then
And then you're going to link a nitrogen. So always put the atom down first that needs the most bonds. Then link to it, form a covalent bond between that one and the one that's next that needs the most bonds. So that's not an oxygen. So it's an N. 1, 2, 3, 4, 5. Well, I'll spread them out. And now what do I have left? A hydrogen. Okay, how many like empty spaces do you see? You see that there's kind of like 5 electrons that are not paired up? Do you see that right now, like nitrogen only has 6, carbon only has 5?
you put it to the one that needs the most bonds.
Okay, so add the hydrogen onto
The carbon.
carbon. Not that color. Hydrogen over here.
And then move those.
This electron in between. This one, that's a double bond. Are you done?
No, you need a triple bond.
Yeah, so in this one, you're actually going to have to take and move this one and move this one. Move all of those in between, and that will end up giving us a carbon. Well, I'll use those for hydrogen. We'll have a hydrogen linked to the carbon. Then carbon's other 3 electrons are then spanned over with the dark nitrogen. 1, 2, 3, N, and its non-bonding pairs are still up there. Can you see those? Can you see how when I moved them? Hydrogen has 2, carbon has 2 and 6, so it has its 8. Nitrogen has 6 plus the 2 above, so it has its 8. That's a triple bond. So this one really shows like all the different things that carbon can do. So how it can form double bonds, it can form triple bonds, it can be a single bond. So carbon has like lots of variety, and remember we were talking that's sort of the organic chemistry aspect to it. So if, where are you? One more. If you're given a name or if you're given a formula, you can figure out, is it ionic or covalent? Just by looking at the name or formula. The kicker is this. Look at the name or formula, look at the first element. If the first element is a metal, then you know it is ionic. Right? So if you see a name like, or a formula like NaCl, you just look at the Na, look at the periodic table, it's on the left side of the zigzag line, it's ionic. Doesn't matter what it is, just look at the first element, compare it to the periodic table. If it's on the left side of the zigzag line, then you know it's a metal. In naming, if you see that the metal is iron, copper, or chromium, those ones are the special ones. Those are those transition metals. So remember, you have to use a Roman numeral. Okay? So like you would have a copper chloride. You would have to say if it's copper 1 chloride or copper 2 chloride. So you need to use the Roman numeral. So like CuCl2. You would see Cu, find it on the periodic table. You know that it's a metal, so you know it's ionic. But if you see those 3, those are the ones that are going to need the Roman numeral. So when you go into the naming, it would be copper 2 chloride. You have to figure out the charge based on the ratio of the charges between them. If not, you just name it. So that's these, right? Iron fluoride, sodium chloride. You just name them. No number prefixes, no Roman numerals needed. You just name them as is. Do put a little note. There are some polyatomic ones. And remember, if you have a polyatomic, it's going to be a nonmetal with a bunch of oxygens. the chlorates, the sulfates, the phosphates, the nitrates. So polyatomics, just name the polyatomic. Don't try and split the name up. So if you see PO4, it's the phosphate. It's not phosphorus tetrahydroxide or anything. It's just the name of the polyatomic together. How do you tell if it's covalent? What is it missing? It's not a metal, right? So if there's no metal up front, then it's covalent. So that's why I say always just look at the first element. The first element is going to be your big kicker. You don't see a metal, then you know it's covalent. Remember that these ones, most commonly, these are the ones you're going to see: carbon, hydrogen, oxygen, nitrogen. So you'll see the CHM, okay? The ones that we were just working on. Those were all carbon, hydrogen, oxygen, nitrogen molecules. You might see phosphorus, you might see sulfur, you might see the halogens, the chlorine, fluorine, bromine, iodine. But remember, it's all those nonmetals up in the corner. So halogens fall into play with that phosphorus and sulfur. Those ones I think of as the minor players. Okay, carbon, hydrogen, oxygen, and nitrogen. Those are your big covalent elements. But if you have two elements and it's covalent, you have to use the number prefixes. So this is where you have to indicate the number of them. H2O2 gets named differently than H2O. So, you tell me. This molecule, KCl, is it ionic or covalent? I heard both. Okay, look at the first element, it is ionic. Right, because potassium is to the left of the zigzag line, it's ionic. This is a metal. And its name? Potassium what? Chloride. Right? It'd be chlorate if it was ClO3. Or, I mean, yeah, if it had the oxygens on it. So if it's just KCl, that's potassium chloride. MgSO4, magnesium is a ionic because magnesium's a metal. Name, magnesium, whole name of the metal. Now the SO4 is a polyatomic, so it gets named according to it. It's the sulfate. So remember the phosphate, sulfate, nitrate, chlorate, carbonate. And then the weird ammonium and hydroxide. Those are the two that don't fit all that. Okay? So CCl4. Covalent. Yep. Carbon tetrachloride. Covalent, you got to use a number prefix. NF3. Covalent. Nitrogen trifluoride. FeO. That is IRC. Ionic. So the base name, you know, with ionic, just the whole name of the metal, first part of the nonmetal plus IDE. But this is one of those three special transition. It's either a +2 or a +3. So remember how you figure this out? So Fe and O, you know oxygen is in group 6, so it'll end up with a -2 charge. So if it's a -2, what does iron have to be? It's got to be a +2 because it's a 1-to-1 ratio. So the charge on the negative nonmetal is going to tell you the charge on the positive metal. So this, Roman numeral 2. So this one is iron 2 oxide. So if you get one of those, you've got to kind of work out what that charge would be. CaCO3, ionic. Yeah, I just wrote it. That's what happens when I hear things. I just start writing what I hear, and then I'm like, wait a minute, what am I writing? It has no sense. Calcium carbonate. CO3 is the carbonate polyatomic ion.
Calcium is a metal?
Yes. Periodic table.
I see it there. I always thought
Yep.
calcium was like a milk.
It is in milk, but it exists as a calcium ion. It exists as calcium +2. gets added to bones, but it's an ionic compound. It's an ion, or a cation, I guess would be the best way to say it. So calcium carbonate. That's what's in Tums. It's not very soluble, though. It's real chalky. LiOH.
That's ionic.
Ionic. Find lithium to the left of the zigzag line. Ionic. And it's lithium hydroxide. Yep, the OH is the hydroxide. Well, in the next chapter it'll be an alcohol, but in this chapter, what? I know. Why? NH4Br. Here's an oddball. Nitrogen, hydrogen, and bromine. You want to say, well, that would be covalent, right? Because these are all nonmetals and hydrogen. But NH4 is an ion, right? So NH4 is the ammonium ion. So that is the oddball. This is the only time, yes, this is the only time that you will see nonmetal first, but it's the ammonium ion. So that makes this ionic because this is a positive and that's the negative charge. So the ammonium ion forms an ionic bond with the bromine or bromide ion. Yep. But for 99% of the time, 99.9, other than the ammonium ion, just look at the first element. If the first element is a metal, then you know it's ionic. First element's a nonmetal, just name it as covalent. Okay? Except for the ammonium ion, that's the oddball. So not terrible, maybe terrible. So we're going to throw in a whole nother thing. So we've been drawing these structures for covalent molecules, but they're three-dimensional. So I brought some balls and sticks. So give like every pair or so, give them like maybe eight gray sticks. Yeah. And like maybe six white balls. A carbon, an oxygen. No, because they come from two different kits. There, here's one of those. So here's some.
What are the other colors?
Just kind of a handful. A couple of reds. One of those. One of these. Yeah, give that to them. They can one of those, one of these, stack of these. Try not to knock everything on the floor. Okay, so what these are to help you see sort of the three-dimensional shapes of molecules. Take those to the back. And you're not gonna have it. You guys got some? Okay.
I'll work on that here.
Okay. So in this, when we draw molecules, we draw them super flat, right? So when we draw molecules on a piece of paper, they look like that. So it looks like there's a carbon, hydrogen pointing straight up, straight down to the left and the right. But that's not actually the case. So I want you to find a black ball with 4 holes. That's carbon. Okay? So can you slide over? Slide over.
This couldn't be carbon. It's the same thing.
No, so that one we're going to talk about. That one's the oxygen, but it's actually, that's some non-bonding. That's the paddles. The non-bonding electrons are the paddles.
Right. Oh.
Okay? So what I want you to do is put 4 gray sticks so that it sticks off of that carbon. So this actually represents really how the electrons are spread out in a carbon atom when they form bonds. They're not going to be straight up, down, and left and right. They want the electron pairs, which are the little gray sticks, they want to get as far apart from each other as possible because electrons are negatively charged. So you have like 2 electrons go back and forth, 2 electrons, 2 and 2, they're all negatively charged, and they want to spread themselves out as far as possible. So that is why they actually start to look more three-dimensional. And so notice, like if you stand it on the tabletop, it kind of looks like there's a gray stick sticking up, and then 3 gray sticks sticking down, kind of like lifting the carbon a little bit off of the table. That is because those negative bonding electrons don't want to be anywhere near each other if they can help it. So can you see it looks like that? Put 4 white hydrogens on the end. Find your white hydrogens. Oh, you did. Okay, so this represents CH4, but this represents truly like what its shape is in a three-dimensional form. So can you see if I hold it like this, can you see how it looks like there's one up, one down, one left, one right? So can you see how that looks? Kind of like how we draw it. We like to draw it so there's a pair of electrons above and below. So when you look at it this way, can you see how it looks like the flat picture we draw? But then when you lay it down, you're like, oh, I don't look like that. Okay? It really doesn't. And so this molecule, these electrons want to get as far apart from each other as possible. The furthest they can get apart is 109.5 degrees. So if you turn and look, every single one of these angles is exactly the same. And so when you stand this up, it creates a shape that has 4 points and it has 4 sides. So can you see that it would be like 1, 2, 3, and the bottom would be 4? Kind of like 4 sides to it, and 4 points where each of the hydrogens are. So this is where this name comes from, because tetra means 4. So the tetrahedral is this kind of 4-pointed structure that a carbon with 4 single bonds will always make. Okay, so they'll look like that. So now, find, you should have a oxygen. Okay, so your oxygen is one that's red, and it only has 2 little holes. So find that one, put 2 gray sticks, 1 in each. So we'll make water. And put a hydrogen on each of those. Mm-hmm. Yeah. So why is that look different? Okay, the angle is different. So you see this is water. So there's oxygen with hydrogens. So what's over here? Those lone pairs. Those lone pairs, carbon doesn't do that. Carbon makes 4 single bonds, 2 double bonds, a single bond and a triple bond. It doesn't make any, it doesn't have any lone pairs. So it's always going to have them spread out. But what you see with oxygen, because, where are you? There. Here, oxygen has non-bonding pairs. Those non-bonding pairs are over on this side. Those non-bonding pairs actually take up more room than bonding pairs do. I just think about like non-bonding pairs, they belong just to the oxygen, so they have to have more space to move around because they don't go back and forth with another atom. So since they're stuck, they actually take up more space, and that actually creates more of a bend to the molecule. Even more of a bend than you would see when you compare these two. It's not as easy to see the difference, but those two, this is actually a bigger angle than this one is. So if you're looking at the hydrogen-oxygen-hydrogen angle and comparing it with the hydrogen-carbon-hydrogen angle, this one's a little smaller. And it's because the electrons on this side kind of push the hydrogens that way. They take up a big space. They have like their own big cloud area, and so they don't spread out as even. So the other one is the nitrogen one. You don't have room. Here it is. The nitrogen one is the purple. You might have a purple. It's a light blue. You might have a light blue ball that has 1 paddle. So I use the paddle to show the non-bonding pairs. So do you see there's 3? Okay, so put a hydrogen on each one. If you don't have enough, you can take that one. Yeah, that's it.
Oh,
You can take it. I was like, give me one here. Right here, put those ones on. And that one's actually gonna make, so put 3 gray sticks and 1 white ball on the end of each.
and a paddle.
Leave the paddle on, yeah. So the paddle, and that's the reason that I like the paddles, is the paddles actually show non-bonding electrons. So the paddles kind of get you to think like there's actually electrons that take up this space, and this space, and this space. So they come into play. So here, this one, this is NH3. This is this one. So do you see this lone pair? The paddle is the non-bonding pair. And in fact, if you really want to think about it, they push these bonding hydrogens a little lower. They take up all that space and they're going to push them down. So what it does is it creates this nitrogen that's a little elevated. It's not flat. It's not flat. It's a little elevated. They call that a pyramid. See the difference in that one. That one, when we kind of compare it to the tetrahedral. So it's sort of flatter looking, but it's still raised a little, and that creates what they call a pyramidal shape. So if you see carbon with 4 single bonds, it's always tetrahedral. When you see nitrogen with 4 single bonds, or nitrogen with 3 single bonds, it's always going to be a pyramid shape because those non-bonding electrons up here take up more room than the bonding electrons do. When you see oxygen,
I think I'm missing something.
Okay.
I see the carbon with 4, carbon is 4 up here, 8 minus 4 is 4, so each 4 electrons.
Right.
So I see the H is 1, so they bond 1 to 2, 4. I see that, that looks nice.
okay,
And the N is 3, the same thing with the.
so nitrogen has
Sign is
5,
3,
so it needs 3 bonds.
so it needs 3 bonds.
So it has 1 to each hydrogen.
One each side. What did that 2 on top come from?
So the 2, because it has 5.
5.
So there's 1 electron, 1 electron, 1 electron, and then 2 to make 5.
Oh.
So 3 that create a bond, and then that other pair is called the non-bonding or lone pair, and they belong specifically to the nitrogen. So same thing when you look at water, when you look at oxygen, there's 2 pairs of non-bonding electrons. And those have an even bigger repelling effect on the hydrogens that are attached to that oxygen. That will always, if you see an oxygen with 2 single bonds, it will always make this bent arrangement. So water's a really good example, H2O. If you see an oxygen with 2 single bonds, it'll always look like it has this bent arrangement. So the thing to remember, non-bonding pairs, they take up space and they will affect the other covalent bonds in a molecule. It'll affect the shape. So they came up with this naming thing. And so the naming thing is, they call it the VSEPR. The valence shell electron pair repulsion. That's what that stands for. Okay? And really all that's talking about is how these bonding pairs and non-bonding pairs will fit around that central atom. So we said with CH4, carbon with 4 hydrogens, right? With CH4, they use a designation, they call it the ABN form, to describe where the bonding and non-bonding electrons exist. So A is whatever the central atom is. So the central atom is always the atom that needs the most bonds. Typically, it's the one in the middle. That's most of the time you can describe it as the one in the middle. So when I look at CH4, the central atom is carbon, okay? B, the B part, talks about how many bonded pairs are on the central atom. And so this one's 4. So you would call this A, B, 4. N is non-bonding electrons on the central atom. Does carbon ever have non-bonding electrons? No. Okay, because it always uses its 4 electrons to form bonds. They might be double bonds or triple bonds, but they're never going to be off by themselves. So you never see them. Carbon never has lone pairs. And so N, these would be non-bonding electrons. And they'd be pairs, not just one. So there's no N in that molecule. So whenever you see something that they say has an AB4 form, it's always a tetrahedral. Always. Carbon with 4 single bonds, always a tetrahedral, it's always AB4. So it doesn't matter if we're talking about a carbon that has chlorines on it, or if it had fluorines on it, or if it had 2 hydrogens and 2 chlorines. A carbon with 4 single bonds is always going to have this shape. Okay, and they're always going to call that the AB4. Carbon has 4 bonds attached, so it's AB4. But now look at your nitrogen. Okay, so if we look at ammonia, NH3, a nitrogen with 3 single bonds, but then has that non-bonding pair. Okay, so how does that one differ in its ABN? So if we had nitrogen, it's got those. There's a hydrogen, and we'll flatten them out just to look at them. But notice when you look at it, it's really more three-dimensional than that. It's just a 1. So this one would be AB3. So nitrogen is the central atom. It has 3 groups connected. And it has 1 non-bonding pair.
So the ends go by
Pair. Yeah, you'll never see a single, right? That wouldn't make it stable. It's always going to have a pair of lone electrons. Like oxygen has 2 pairs, nitrogen has 1 pair. Because 1 single one, that would be super reactive, right? That wouldn't be stable enough to make it stay. Okay, so remember that non-bonding, this will always be pyramidal. It's always going to look, so it doesn't matter if I have chlorines or fluorines here, or hydrogens here. A nitrogen with 3 single bonds is always going to take that pyramid type of shape. You have water. Here's oxygen dichloride, and oxygen with 2 chlorines on it. So it's shaped, if we look at the oxygen, if we say the ABN for it, if oxygen is A, how many groups connected? 2. How many non-bonding pairs? It doesn't matter what's around the chlorine. It matters what's around the central atom. So when you do this, you're only looking at the one in the middle. So this one, you have, if the oxygen's in the middle, it has 2 groups connected and has 2 non-bonding pairs. So it'd be called AB2N2. And that is always going to have a bent shape. So carbon, nitrogen, oxygen, those are big covalent bond formers that we've been like doing little diagrams and stuff for. So what about CO2? I made 3 CO2 molecules. Do you have one? Look on your pile of stuff. Do you have a molecule that looks like carbon dioxide? Anyone? Huh? Took it apart. Terrible.
We need it for the carbon.
Yes. Do you see the carbon in the middle? Do you see the 2 oxygens? Okay. So you see in this one, carbon in the middle. Carbon has 2 electrons on either side. Up, come back. Where are you? Here. Okay, oxygen on this side, 1, 2, 3, 4, 5, 6. Oxygen on this side, 1, 2, 3, 4, 5, 6. So you have that one. Do you guys have one?
No, well, we
Take it apart.
But we had 2 to build up. We only had 1.
They've got one, okay? So in that one, just to look, so if we have carbons in the middle, we're going to say it's the A. How many groups does it have connected? It doesn't matter if it's a single bond, double bond, or a triple bond. How many groups? So how many groups does it have connected to it? Just two. It has two oxygens connected.
So you mean as elements?
Like it doesn't matter. It can be a group connected, could be by a single bond. A group connected could be a double bond, or a group connected could be a triple. Okay? So you would say that that carbon has two groups connected. It has two things connected to it. Irregardless of electrons, it has a group connected here and a group connected here. Okay? So if you have electrons and there's only two groups connected and they want to get as far apart from each other as possible, what's the furthest distance they can be apart? On opposite sides, which is exactly what that one looks like. Right? So see the carbon in the middle? See how the oxygens go to the opposite sides? There's double bonds to each oxygen. AB2 is going to create this 180-degree separation of each other, and that's going to make something that is linear. Do you see how it looks like a line? So it goes straight across. Okay, so carbon, CO2, good example of a linear molecule. That hydrogen cyanide that we did, HCN. Can you see how that's linear? That carbon in the middle has two groups connected. So it would just try to get you get those electron pairs as far apart as possible. They'd be on opposite sides of each other, and you'd end up with a linear molecule. You don't care about these non-bonding electrons out on the oxygen. You only care about the ones that are connected to the center. Okay? So when you're looking at shapes, you're really just looking at the center atom. How many bonding groups, how many non-bonding pairs on that center atom? Okay? Only one more. So the last one, I told you this one. Water will always be AB2N2, and it's always going to look bent. It's always going to have that bend to it. When you look at the water molecules, take your water molecule. Okay? But now you might draw it, and it might look like this. Do you see how it looks like the oxygen and the hydrogen went up and down? If you just turn it, so is it wrong if you drew it that way? See how if I hold it this way, see how it actually looks like it's like straight in a line? But you gotta lay it down. Okay, so that way you can actually see the bend to it. And it's because of those non-bonding electrons on those sides. Last one, there's only 5. There's more than that, but we're not doing anymore. Okay, so the last one was formaldehyde, CH2O. Carbon's in the middle. And then it had 1, 2, 3, 4. Remember it had to double bond to the oxygen? 2, 3, 4. So that would give oxygen its 8. And then it had a single bond to each of those hydrogens. Yes? And I'll take your carbon dioxide. I'll make it into so here's this. Carbon in the middle, single bonds to the hydrogens, double bond to this oxygen. Okay, does everybody see that? When you look at it, what shape is this? It's like what? Huh? It's not a pyramid. Look, it's really flat. Okay? I can actually like lay it down on the flat. It's flat and it has 3 points, which is a triangle. So they call this one trigonal pyramid or planar. It's flat. So when I look at it, see how it looks like it's flat like a piece of paper. But I see that there's 3 points. So this is trigonal planar. 3 points and it's flat. Each of these is 120 degrees. You know, a whole circle is 360. So this would be 120 degrees, 120 degrees, 120 degrees. So that's called the trigonal planar. That's the 5th one. That's kind of like the most complicated one.
Is that AB4?
No, it'd be AB3. Right? Because carbon in the center has 3 groups connected, no non-bonding pairs. So now you're, okay, go.
Oh.
Did you have a question?
Yeah, well, so
Okay.
like if you were to take like sodium bicarbonate, for example.
Okay, NaHCO3. And?
CO3, right?
Uh-huh.
And And that's how you would write that out, but how would you build that?
So in the drawing, I mean, I can show
That's
you,
weird.
but you don't have to learn that for a test.
Okay.
So do you want me to draw it for you?
No, we won't waste
Okay.
time.
So the ones that I would say to stick with, these examples are good examples of three-dimensional shapes. The book gives you a chart that looks just like this, and this looks just like the ones that we have done. Okay, so seeing this first one, I apologize, you'll have to, like, maybe it'll let me zoom. You know how sometimes it does this? And then sometimes the gray goes away. Sometimes it doesn't. Okay, so in that, so you have AB4, CH4 is a great example, tetrahedral. Okay, AB3N, NH3, great example, pyramidal. So use this chart to sort of like look at and get your comparison. And we're just going to stick to these simpler ones. And there was really a reason to go through this because you're like, why do I have to know what these shapes are? Okay, and it all has to do with sharing of electrons. So in this, just so you know, so the CH4, it is an AB4, and it's always tetrahedral.
So their shapes are always in that format.
Yep. So the AB3N, that is the pyramidal. Great example is NH3. The AB2N2, water, H2O. Great example, always going to be bent. AB3, that was the formaldehyde, CH2O. And that one's the one, it's trigonal planar. So you can see it looks like a triangle and it's flat. And then the last one we were looking at, CO2. That one's AB2 and it's linear. So it just ends up forming like a straight line, like a pencil. So the reason for talking about this is the fact that nonmetals do not always share very well. Nonmetals, especially nonmetals that are up in that upper right-hand corner, they hold on to their electrons and do not share equally. So you know how we were drawing them and we said, okay, well, if you have a carbon and you have a hydrogen and we put the electrons so they look like they're perfectly right next to each other, that's not always the case. Some nonmetals are what they call electronegative. And if you look on the periodic table, it's these: nitrogen, oxygen, fluorine, and chlorine. We're going to talk about these until you're like, why? All the time. So you see these, they are the small upper right-hand corner nonmetals: nitrogen, oxygen, fluorine, and chlorine. They hold their valence electrons really tight, and they pull electrons in that they're supposed to be sharing. So while hydrogen would share these exactly in half because they have the same attraction, if you had hydrogen and chlorine, all the electrons will be like this. Chlorine pulls the electrons closer to it instead of sharing equally. And it's these four that cause all the trouble. Okay? So nitrogen, oxygen, fluorine, and chlorine, when they form a covalent bond, they're going to try and pull the electrons in closer. But now you know those electrons are negatively charged. So here, do you see how this is very neutral? The electrons are even. The electrons are half and half. So you would say that those two hydrogens are very neutral. But what about that hydrogen and chlorine? The electrons hang out more where? On the chlorine side. And electrons have what charge? Negative. So this side becomes slightly negative. This side, as a result, becomes slightly positive. It's just that they don't share evenly. I always think of like, people get divorced and you have the primary custodian parent. So the electronegative atoms, they're like the primary custodians. They're like, you're going to stay with me most of the time. You only go over there a little bit. Same thing. Because they have a small atom, their valence electrons are close to the nucleus, And that creates more attraction for those protons in the center. So the electrons want to hang around those little nonmetals, nitrogen, oxygen, fluorine, and chlorine. The other nonmetals do this a little, but not as much. So they use this weird symbol that you've probably seen before. It looks almost like an 8, it's called a delta symbol. It looks like an 8 that's not closed at the top. They use that to describe that slight positive or negativeness, and that's what creates polarity. So in looking at a chart that shows these, don't have to memorize any of these numbers. They gave them electronegativity values. The higher the number, the more electronegative. So when you look at the metals, do you see how little their electronegativity is? That's why metals just give up their electrons. They're like, we don't even want them. Because if they get rid of their electrons, then their next layer in is full. So look how low lithium, sodium, potassium are. Extremely low electronegativities. But then look at the nonmetals over on that far right. See where all the nonmetals are more than metals. But when you start getting to the nitrogen, oxygen, fluorine, and chlorine, they have electronegativities of 3, 3.5, even 4. Fluorine, far and above, fluorine is the most electronegative because it's the smallest, and it has 7 out of 8 electrons to create stability, so it pulls them in super tight. And it does not share well. When it's in a covalent bond, the electrons stay with the fluorine more than they stay with whatever they are bonded with. So the significance with this is that you can end up with even sharing of electrons, nonpolar, or you can end up with uneven sharing of electrons, polar. So when you think of polar and nonpolar, what do you think of when you think of something that's polar? What's a super example of a polar molecule? Water. And water is really like the best example because nitrogen, oxygen, fluorine and chlorine, oxygen's right next to fluorine. Oxygen's got a high electronegativity, it's 3.5. So when a water molecule forms a covalent bond with hydrogens, the hydrogens, they don't really keep their electrons so much. So you can kind of think of it looking like that. So the oxygen's like, boom, pulls the electrons towards it. The hydrogens have less interaction with their electrons, enough to maintain stability. But it's going to create this slight imbalance. So what happens to the oxygen side? It becomes slightly what? This side becomes slightly negative because the electrons are pulled over to that side. That means the hydrogens become slightly positive. So the hydrogens, because they don't have their electrons evenly shared, become slightly positive. Carbon and hydrogen. What we just did, CH4. Polar or nonpolar? You're looking for nitrogen, oxygen, fluorine, or chlorine. Do you see one of those? No. If there's no nitrogen, oxygen, fluorine, or chlorine, nonpolar. So for polar, look for 1, nitrogen, oxygen, fluorine, or chlorine. That's the big odds-on favorite. If you look at a molecule and like, oh, there's 1 oxygen, polar, move on. Okay? You look and you're like, oh, there's 1 fluorine, polar. Okay? Especially if there's just 1. Because that 1's always going to create that somewhat lopsidedness. So like ammonia, NH3, 1 nitrogen, polar, move on. Okay? With they're small and there's only 1. If you see nothing but carbons and hydrogen, nonpolar. This is methane. What is the significance of methane? Cows make it. What is this? What else? What do we use that for? Fuel. All your fuels, all your gasolines, oils. What do you know when you take oil and water? They don't mix. And it's because of this. Water is polar, and water likes to mix with stuff that also has that slight positive negativeness or charge. Water dissolves salts. So water can mix with those too. So salts and water, polar molecules can mix. Non-polar molecules, they literally get pushed out of the way because they're too neutral. Their electrons are too uniformly distributed, and that's why polar and non-polar things don't mix together. So I kind of gave you a list. Where are you? There. Gave you a list of things that are polar, things that are non-polar, just to kind of help you like link them together. So you might be able to add some things to this too, but I said remember water. NH3, this is ammonia. And like I said, if you see a nitrogen, oxygen, fluorine, or a chlorine, if you see that, it's NH3, it's ammonia. If you see that, then you know it's polar, especially if it's small. I tried to give you some small looking molecules. So sugar is C6H12O6. 6 oxygens there. We'll look at carbohydrates more and you'll see there's lots of oxygens sort of scattered throughout, creating all their little polar regions. Vinegar. Vinegar is CH3COOH. 2 oxygens on one side of a molecule, that creates a polar area. Nitrogen, oxygen, fluorine, and chlorine. So you know you can take vinegar and water, mix it together, and it mixes. Okay? You can take ammonia and water, mix them together, and they mix. You can mix ammonia and vinegar, it's just going to be super smelly. Okay? But you could take sugar and put it in water, stir it up, mixes. So when you have things that have similar polarity, they'll mix together. Salts can dissolve in water because they have a charge. So that's super polar, okay? So being a charged ion is going to allow it to interact with water. But then look at the nonpolars in the list. Nonpolars in the list are missing nitrogen, oxygen, fluorine, or chlorine, or they have an even arrangement of them. So Cl2, O2, N2, all those diatomic elements, all nonpolar. Chlorine, there's 2 of them. They have to evenly share. Even though they both want to pull electrons, they have to evenly share because they're the exact same atom. Methane, gasoline, grease, oils, candle wax, all examples of non-polar molecules, butter. So you can take like olive oil and butter, if you melt them, warm them up, mix them together, what do? They mix together, fine. Okay? They don't separate out because they have the same polarity. Polar things mix with polar things. Non-polar things mix with non-polar things. But if you try to mix these 2, they're going to separate out. You have to do special things to make them stay mixed. Okay? So we will talk about this again when we start talking about solutions. There's only one other topic to cover. So there's stuff about polar, stuff about non-polar, how ionic falls into that realm. The last thing. I don't know why they added this one in here. They could have put it in chapter 8. It would have been fine. So this is they talk about a counting unit. So the counting unit is called the mole. So chemists could not talk about one molecule of something because it's so super, super small. You'd have all those exponents, lots of decimal places. So they were like, we need to talk about a countable number. So just like you know that 1 dozen is 12, so that is a given unit. Scientists sat down and said, okay, if we had 12 grams of carbon, which has an atomic mass of 12, if we take 12 grams of carbon, how many molecules or atoms of carbon would that be? So they sat down and did the calculations, did the calculations. And so Avogadro said, I got it. It's a really, 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 really big number. So we put it in exponents here, okay? So Avogadro studied this and determined that there are 6.02 times 10 to the 23rd particles of anything in 1 mole. So 1 mole equals 6.02 times 10 to the 23rd molecules. And it really doesn't matter if you're talking about molecules of carbon, molecules of water, molecules of methane, molecules of vinegar. If you're talking about units, you have 6.02 times 10 to the 23rd units in 1 counting unit of the mole. And it would be equal to the formula mass of that molecule. So like we said with carbon, we said that if you collect 12 grams of carbon, there's 6.02 times 10 to the 23rd molecules of carbon in that sample. And that would weigh 12 grams. So this formula mass is just the mass, the atomic masses of all the atoms in the formula with grams at the end. You just add them up. So they use this because now that's a countable number. I can weigh out 12 grams of carbon. I can weigh out 18 grams of water. Okay? I can't weigh out 1 molecule. So they just had to scale up. They had to scale up to something that's measurable, and that's where the mole comes in.
So nitrogen would be 14 grams.
But if I had N2, that would be 2 atoms of nitrogen, so not 14, it would be 28 grams.
20, okay.
Because it's based on what that formula is.
Okay.
Okay, so that's what they said. They said, okay, if you have off the periodic table any element, so for silver, if I weigh out 107.9 grams, that's 1 mole.
And that's what I was trying to get at with it.
With carbon, if I weigh out 12.01 grams, that would be 1 mole. So the formula mass, or the mass on the periodic table, that's what you would do for an individual element. And notice that that would be 6.02 times 10 to the 23rd atoms. Okay, 1 mole is 6.02 times 10 to the 23rd pieces of whatever we're talking about, and it would be equal to its formula mass. So what if I have... So it's kind of like mole is allowing you to look at grams, and mole's allowing you to talk about molecules. So it's allowing you to think about that small scale molecule, but it's also allowing you to think about a measurable amount in a mass.
Okay, so I look at this number, let's say for example, what's each one? 10. If I look at oxygen at 16.
Right.
That tells me that if I get, I did something before. If I get 16 grams of that.
Right.
If I get 16 grams of that, that's equal to
1 mole.
1 mole?
Mm-hmm.
And 1 mole means?
That I have 6.02 times 10 to the 23rd atoms. If I'm talking about individual atoms. If I'm talking about O2, then I actually have to figure out how many oxygens their mass is.
A mole is the number of atoms.
A mole is a countable, like it's a gram formula mass of a molecule. A mass in a mole is that 6.02 times 10 to the 23rd particles. Because it could be atoms or it could be molecules. It depends on if, like with this, we're talking about atoms, right? Yep. So if you're talking about silver, you're just talking about individual silver atoms. But what about when we talk about water? So we can put moles of water. But if we're talking about water, there's 2 hydrogens and an oxygen. So in that, we're talking about a molecule, okay? Versus an atom. So an atom is typically just a single piece of 1 element. Whereas a molecule, you can have more than 1 element chemically combined, like water molecules.
Well, this means 16 grams of oxygen is equal to 1 mole.
Right.
And 78.96 molecules of SC is equal to 1 mole.
Right.
And the mole for that, what we count there is atoms because it's 1 element. And
correct.
You count in that 1 element are the atoms.
Yeah. So you can go back and forth between those. So it really just allowed them like a way to be able to measure stuff. Because you can't talk about it in this super, super small size. You have to be able to have something that you can actually like weigh out on a scale. So like when in lab, when we go weigh stuff out, you're measuring out billions of billions of billions of molecules. But you can't measure individual molecules. It's just too small. So we went to this larger size. So in this, 2 ways that you do these conversions, and it's just 1 step. If you have grams or moles, you can convert from grams to moles as long as you figure out the formula mass. So both of these, you want to use what is known as the formula mass. The formula mass is the mass of each of the atoms in the molecule with grams at the end. So if I have CH4, how many carbons? One carbon, and each carbon weighs 12. And you could put 12.01. We'll just round to whole numbers. We're not going to get super uptight about that. So that's where I get 12. We have 4 hydrogens. Each hydrogen weighs 1. Okay? And you'll always have a periodic table. You don't have to memorize this. You just remember you're taking the mass, round to the nearest whole number. Okay? So this is from the periodic table. And then just round. For us, round to a whole number. So 12 plus 4 is 16. So there is 16 grams in 1 mole.
Times the 3 moles.
Yep, so if I want 3, just take 16 times 3. It's a single step. You can think of it from that way. If you want to use it so units convert, you always put the unit you start with, times in the line, moles goes on the bottom, just like we were doing, like when we were doing other unit conversions. The unit you start with goes on the top, and the unit you start with goes to the bottom in the first, grams goes on top. And so you see that there is 16 grams in 1 mole. See, moles and moles cancel, so it's 3 times 16. 48. It's just 1 step, but it won't ever be more than 1 step. But if you have grams and moles, that's how you figure out. That's how you go from grams to moles or moles to grams. You just use the formula mass. So if I have 100 grams of CH4, how many moles is that? So I'm going to go back and use 16 in 1. So if I have 100 grams times, what unit goes on the bottom? Grams. So moles goes on top. So notice the unit I want on top is just a single step. And it's 16 on the bottom, 1 on the top. So that's this formula mass. 16 grams over 1 mole, or 1 mole over 16 grams. I can use it either way. 100 divided by 16, 6.25. And we'll say it's 100 exactly. So we can keep our, I didn't write significant figures, sorry. Okay, so if you have grams, you can go to moles using the formula mass. If you have moles, you can go back to grams just using the formula mass. And if you want to make sure you don't multiply when you need to divide, just set it up like a unit conversion. So whatever you're given, that unit goes on the bottom in the first step. The unit you want is going to go, or the unit you want is going to go on top. And that way you will always multiply if you need to, or divide if you need to. Last one, we said that we can go moles to grams and grams to moles just by using the formula mass, but we can go from moles to molecules. We can go from a nice measurable number to a really humongous number if we use Avogadro's number. 1 mole is equal to 6.02 times 10 to the 23rd molecules. So I can use those as being equal. So if I have 3 moles, I can go to molecules by multiplying times Avogadro's number. So 3 moles times 6.02 times, no, not down there. 6.02 times 10 to the 23rd. So molecules goes on top, that's the unit I want. Moles goes on the bottom so that they will cancel. Then you just multiply. So here, making sure you put it in your exponents. Putting it in the calculator is the biggest trick with this one. So 3 times 6.02 times 10 to the 23rd is 1.8 times 10 to the 24th.
So only time it'll be 2 steps when you do grams to moles.
Yeah, but I won't do that. We'll just stick with 1. So if I give you moles, I could ask you molecules. If I give you moles, I could ask you grams. So it's only just a one single step each time. So it's just a matter of reading the question and going, oh, moles and molecules, I got to use Avogadro's number. Or, oh, grams and moles, I got to use the gram formula mass. Yes, you probably should to 2. But I should have put better numbers in here. 1.3 times 10 to the 21st molecules. If I want to go to moles, what unit do I put on the bottom? So molecules goes on the bottom, moles goes on the top. 6.02 times 10 to the 23rd. I have one. I didn't bring the whole stack. I totally forgot. Slack. 1.3 EE21 divided by 6.02 EE23. I got 0.002159. 0.002159,468 moles. That's all the numbers. But what should I round that one to? So 1.3 times 10 to the 21st has 2 significant figures. 2 significant figures, so I would round this to here. So what would happen to that? It'd be 0.0022. Okay, in the rounding part. Like the top one, I should have rounded that to 2 times 10 to the 24th if I'm going to stick with 3. 3 is just like, that was just a bad number. I should have put 3.0. Okay, so this finishes chapter 3.